astrophysicist. Coming up, Cosmic Queries edition of StarTalk. This one on X-rays in the universe. This is StarTalk. I'm your host, Neil deGrasse Tyson, your personal astrophysicist. And today, it's a Cosmic Queries X-ray Imaging Astrophysics edition. You didn't think we had one of those, did you? Well, we did, because we have one of the world's experts in that very subject sitting with me right now. I've got with me Kim Arcand. Kim, welcome.
Thank you.
I got to get your title correct here.
It's a long one.
Visualization and Emerging Technology Lead for the Chandra X-ray Observatory.
Yes.
Wonderful. And they didn't just pull you out of the ether. You've got some chops. I'm holding your book called Magnitude, Scale of the Universe. And I love this. On the cover, it's got a mouse, a human brain, a bowling ball, a hot air balloon, and Earth. It's like, what scales are they? And you open the book, and it lays that stuff out. And it talks about when things are big and small and how to think about them relative to one another. And this is stuff we confront every day in modern astrophysics. Cool. How do you wrap your head around the scale of things? And you need to visualize it to know how to do it best, because otherwise we fumble ourselves trying to explain it. And so beautiful book.
Thank you.
And thanks for bringing a copy here. And my co-host, Chuck.
Hey, Neil. How are you?
Welcome back to StarTalk.
Absolutely. It's a pleasure. Yes.
All right. And you're tweeting at Chuck Nice Comic.
Yes.
And you're Instagramming at?
Kimberly Cowell.
Kimberly?
Cowell. K-O-W-A-L. It's my maiden name. Just had to throw that one in there.
Why you got to do that?
It's from an old Yahoo email. Don't ask.
Oh, okay. So Kimberly
Kimberly Cowell.
Yes. K-O-W-A-L.
Kimberly Cowell.
Cowell.
Okay.
Yes.
Yeah. But since you're a visual person, Instagram, we got some kick-ass images.
Yes.
Yeah, so we're going to all look for that.
That'd be fun.
Yeah. So you got some questions for us, Jack.
Absolutely.
Let's do this.
Yes. You know, we have, of course, solicited questions from all over the interwebs. And we got some good ones here, but we always start with a Patreon patron, because Patreon patrons give us money.
Oh,
right.
Yeah.
And since we are cheap whores,
I'm slowly getting used to that.
Yeah, you don't like that. You don't like anything to do with money.
No, just money.
This was my idea. I'm like, give us money. We'll do whatever you want.
All right. First question.
All right, first question. What would be the most exciting find that you would have via X-ray telescope? Like, what would be the piece de resistance, so to speak? This is what he says. Okay, this is Jesus, who from Patreon.
Patreon, okay.
Jesus.
Well, I mean, I think there's a lot of, if you ask that question of a number of different people, there'd be a lot of different answers. I think, like, for me in general with astronomy,
You're making the images, so you get.
I know, I do.
You get top pick here.
I get top pick. It's too exciting.
Yeah.
For me, just with my biology background, anything to do with finding life, possibility for life on other planets. I mean, when I first started working for Chandra, exoplanets weren't really a thing. Like, this was like the late 90s, and they weren't really. I think maybe there were one or two discoveries at that
the
time.
first was 1995.
Right,
so,
exactly.
Yeah.
So
they're all the rage now.
Yes, they are all the rage. Now there's thousands of them, I think. And Chandra has some really interesting capabilities to study, especially the effects of the host star and how that might have habitability issues with its children planets. So I think anything to do with exoplanets, for me, that would be super exciting.
So this is extra information brought to us by X-rays.
Yeah.
About these objects we already know of.
Right.
How about objects that we would know nothing of were it not for their X-ray signature?
So,
all
right.
Would you put at the top of that list?
Oh, all right. Well, I think...
Because really, your X-rays for exoplanets are supplementing other data.
They're helping the bigger puzzle.
The bigger puzzle.
Yes.
Give me one where the X-rays are the only pieces in the puzzle.
Well... So I'm too much like a multi-wavelength astronomy junkie here.
Oh, wow.
I
Look
can't.
at that.
I know.
You're asking me to choose one of my children.
That's exactly how
This is the Sophie's choice.
And I would never pick one of my kids over the other. And they're listening, so I know that for a fact. So anyways, but yeah, I feel like these days it's all about how the different kinds of light are each one tool in the toolbox of astronomy, right?
Very good.
And it's truly about how all of those pieces fit together. So X-ray astronomy complements really well with radio astronomy, with optical. I mean, it's hard to pick just one.
Okay, so this is the healthiest way to think about that.
Yeah.
That you are a cog in a wheel, a
Right.
puzzle piece to a larger, organized understanding of the universe.
Right.
Yeah, I mean,
and with the addition of like gravitational wave science,
A
like
whole new
that's
window.
That's
yet
a-
more.
yeah, that's
so
a-
multi-messenger gets exciting. I mean, there's a lot to go there. So I can't just pick one.
can't pick one.
No,
All
can't
right,
do it.
There you go.
All right. There
Can't
it
just
is.
have one.
Nope.
There you have it. I like the
And are you showing off your cell phone here? Look at
Maybe.
Look at that.
It's beautiful.
Okay.
This
your
is
cell
That is
phone.
actually-
gorgeous.
So that's
This
a
is an
skin.
image.
That's or cover.
It's a little case. It's a little,
little case.
And this is NGC 602. It's a beautiful stellar evolution area. Baby stars being born.
Stellar
And
nursery.
stellar nursery. Lots of babies in there. And so you've got this. The purple is the X-ray data from Chandra, and then there's also some infrared data from Spitzer and some
Chuck, are you making
optical
crying
data
babies?
from Hubble.
That's my baby star. That's my baby star.
And I just randomly found this on Amazon one day, which was, I think, so cool. And I was like, I know that image.
Because
602, because I worked on it.
you created that image.
All
Well,
right.
with a team.
With
I
a
mean,
team, yeah.
nobody, one person
Sure,
does anything.
sure, of course.
Right. Yes. That you scientists are always so damn humble. You know what I mean?
You can't be, otherwise we'll smack you down because you could be
I
wrong
guess
next
you,
week.
Right.
Exactly.
Right.
And you're in the doghouse.
Exactly.
Oh, yeah.
Yeah, and you guys kind of all need each
Nature's
other.
always more clever than any of us.
Right.
Right.
Yeah.
Yeah.
Well, there you have. That's
For
a.
sure.
Oh, I like that. Nature is always more clever than any of
Oh
us.
yeah.
Completely
yeah.
agree.
Yeah.
Yeah.
And sometimes it's more clever than all of us combined.
Wow.
Yeah.
So one thing. So just to emphasize, your X-ray data is part of other data that's combined to make that image.
So multi-wavelength astronomy, again at its best. This
There
is
it
kind
is.
of a great observatory classic with Chandra, Hubble, and Spitzer, which I think is really beautiful, and it just helps tell the story. You know, X-rays I think are
Right.
thought
Just so
of.
Chandra's X-rays.
Right.
Hubble
I was-
is obviously visible
Optical,
light,
typically.
and
Spitzer's infrared.
Spitzer's infrared. So
Yep.
two very different branches of the spectrum.
Oh, very much.
But
yeah.
combined to make one image, as
image.
though
Right.
our eyes could see that
Right.
broadly.
Right.
So if you had sensors in X-rays, visible, and infrared, like
You'd be able to put this all together.
and you'd look up and you'd see that.
you see
Right.
that.
Right.
So
Right.
if you were Predator, you could actually
Predator could
enjoy
do
that.
or
Right.
or Geordi
Or
on
Geordi
Star-
LaForge on Star Trek.
Yeah,
Correct.
That's
Right.
cool.
Yeah.
That's cool.
Yeah,
Yeah.
you,
Yeah.
you could tune that sucker up.
Yeah.
You know, Geordi had the opportunity not to be blind, and he turned it down.
Really?
Yeah, in an episode of
that.
Star Trek. You know,
missed that one.
and I think it's because he actually saw your image.
That's probably it. Nice.
Well, the thing is, we are practically blind when you consider how narrow is the slice of the electromagnetic spectrum our retina
Absolutely.
shows us. We are practically blind.
Wow.
Yep. We can see so little, just
If-
like a
if-
tiny
if,
sliver.
You know, you open a book and it has the rainbow. You know, the colors of the rainbow: red,
Right.
orange, yellow. Roy G. Biv.
Right.
Red, orange, yellow, green, blue,
Blue,
indigo,
indigo.
violet. Can't forget indigo.
Yes.
Right. And so it fills the page, and then but you look at the entire range.
Right.
And I'll recite that now. It goes from high energy to low energy. You go from gamma rays,
Right.
X-rays, ultraviolet,
Right.
violet, indigo. You do Roy G. Biv backwards, right? Violet, indigo, blue, green,
Green, red.
Yep.
No, green, yellow, orange, or orange, yellow, red.
Okay.
Okay. Then you come out of the red, you get infrared,
Infrared.
and then you get microwaves, and then you get radio waves.
Wow.
When you put all that on one page, visible light is this tiny,
It's a tiny little sliver.
Sliver.
So if you have like a piano in front of you, it'd be like human vision is middle C and maybe a couple keys around it. That's it.
Yeah, barely an
All
octave.
the rest of the keys.
Not quite an octave around
Now,
middle C.
so are there
would make it
any?
very-
So imagine listening to Beethoven's Ninth Symphony,
Which is like
which is
three
hammered
keys.
out
with
on
three
8 keys.
keys.
Yeah.
Very
wow.
boring.
Yeah, that's terrible.
Yeah, so we're basically blind. So he did the
I
right thing.
hate my eyes now.
I know.
No.
They're pathetic.
God, I hate my eyes. So let me ask you this then: are there any animals that see
Oh yeah.
outside of the spectrum?
Oh yeah.
Deer?
And deer?
Deer can see a little bit in ultraviolet.
A little ultraviolet.
Insects are told all about
Insects,
ultraviolet.
Right.
Bumblebees.
Yeah.
Oh,
And you-
bumblebees
and-
see in ultraviolet as well.
Yep, a little bit.
And you know that they like ultraviolet. Okay. This is how we know we are smarter than insects.
Okay.
Okay. Evidence we are smarter than insects.
All right.
Okay.
Cool. No one
know-
is stepping on us to kill us. No, go ahead.
we invented bug zappers. which are intense in ultraviolet.
Ultraviolet, and they
So they say, I can't stop it.
right,
Zap.
exactly.
And that's how we know we are smarter than they are. And bug bulbs, which you don't see much anymore, they're
Right.
kind of amber.
Right.
They don't repel bugs. Bugs don't see it. So their entire sensitivity to light is shifted towards the blue end into the ultraviolet, and it dangles off the other end some red and orange. So it's not that they avoid the red bulb over your picnic table. They don't see it at all.
They can't see it at all.
Yeah, and if you put a bug zapper at the end of the lawn,
Right.
they all go to the bug zapper. So I just want you to appreciate that we are smarter than bugs.
So the alien invasion comes and it's bugs. We should just rely on our zappers.
Oh, good.
Is that what we're thinking?
Right.
If they are
Is that-
bugs.
Yeah, but you
That
know
seems
what? If
viable.
an alien invasion, if they were smart enough to get here and we're too stupid to leave here, something tells me they're going to have the equivalent of a bug zapper for us, like a concert.
Yeah.
Where we, just like, oh my God, free concert.
Yeah, free concert and good food.
Right,
Yeah, we all
exactly.
go.
Free concert and hamburgers. What?
Right.
We
Zap.
walk in and zap. Right.
That'd be bad
And no
for
one
us.
comes out to tell you not to go.
Exactly, because
Right?
everybody got zapped when they
Everybody
went in.
got zapped.
Dude, that must be the best concert ever. It's been going on for 6 days and nobody's come out. Yeah.
That wouldn't be fun.
Yeah, we would be putty in the hands of a smarter species, for sure. All right, next question.
All right, here we go. Pentybot on Instagram wants to know this. Since you guys were talking about the different types of light in the spectrum, what is the difference between Chandra X-ray Observatory and James Webb Telescope? Is it just the spectrum of light, or what else do they do that is different?
Let's start out with the orbit. So what
Sure,
orbit
sure.
is Chandra in?
So Chandra's in a highly elliptical orbit that goes about a third of the way to the moon. Chandra's about the size of a school bus. It weighs maybe 4,800 kilograms, something like that. And
On Earth.
Yes, exactly. Exactly. Very important
On
detail.
the moon, it weighs 1/6 of that.
You know,
Okay.
actually, interesting thing about Chandra is it was, I'm pretty sure still was, the heaviest thing that the space shuttle ever launched.
Really?
And
Wow.
the fact that it was so massive meant that, and I didn't actually learn this until many years later, the fact that it was so massive meant that it was a more riskier ride for the astronauts than it would have been with a lighter payload.
Right.
Their abort scenarios, for example, were more challenging, but I didn't know that at the time. So, yeah, so Chandra was large and in charge, and it was
I like
fortunately perfect.
Large
Everything
and
went
in charge.
perfect to get it up into space. Thanks
And
to
so
the
that's that
astronauts.
orbit. And so James Webb is 1,000,000 miles on the other side of the moon.
Right.
So they want that away from Earth interference.
Right.
Yep.
So James Webb is an infrared-based telescope. And again, different parts of the spectrum were
Yeah.
tuned differently. And so they have their targets of interest. Their objects of affection in the universe are different.
Yeah.
But then you bring them all together and you get the
Right.
full, the
So
full
now
picture.
you mentioned the orbits. This is a question coming from Chuck Nice on Facebook.
Chuck Nice,
Chuck
in
Nice
person.
here in the office.
Oh, wait, let me just comment about. I'd say something a little more about James Webb.
Go ahead.
So Chandra's in this big elliptical orbit, so it's orbiting Earth.
Yep.
James Webb is in a Lagrangian point.
Ah,
It is a point where all forces that would otherwise move it are stable.
right.
And so you put it out there, and it takes very little station keeping to just keep it there. And this is these famous Lagrangian points are where we imagined you'd build stuff.
Right.
Because you just get all your hardware, just load
leave
it there.
Right.
You leave it
Just
there.
it'll just hang around.
Just hang.
It's
Right.
the garbage patch of the solar
it's what
system.
It is. It'll collect it. And
Right.
I need a bolt or a screw. There it is.
Right,
It's
and just
floating right
hangs
by.
hangs right there.
It doesn't fall to anybody's
Right.
surface.
Yeah.
So they were imagined to be a little more useful than they've turned out to be. It turns out we can make things that are orbiting. It's not that hard. Because once you bring something up into orbit, it orbits with
With
it.
you.
Yeah,
Right.
yeah. So
Right.
it's not. But anyhow.
Although I do love the Lagrangian point, like as a place, like
It's
you know,
a cool name.
It's
Yeah.
a total cool
You know?
name.
Yeah,
Right?
Exactly.
Lagrange.
Yeah.
Lagrange.
Yeah.
All right, so now let me ask you this.
Okay.
As these orbits happen, are they staying on a fixed point, or are they observing different quadrants as they move around?
So Chandra goes a third of the way to the moon at its farthest point, and then
Okay.
goes about 16,000 kilometers to Earth at its closest point. So it's this nice elliptical orbit. And they did that for like optimal observing capability so that it has the most time to essentially be looking out at the universe.
Gotcha.
But, you know,
Far away from Earth.
far away from
Yeah.
Earth, exactly. But yeah, I think what's really interesting about, well, for one thing, I think it must have gone like 2.7 billion kilometers by now, over 20 years, which is, I think, fantastic. And you think about it, like Chandra's never had a day day off in like 20 years. Doesn't even have like an hour
She
off.
works
or
hard
anything.
for the money.
Right? I know. And how perfect that had to work when it was launched. So anyways, but I'm not sure what James Webb is doing, but.
Right. So, well, it's not up yet, of course.
Well,
right.
true.
At the
When it
time of
goes.
this broadcast.
Yes.
But so these things have gyros that enable you to know where you are and where you're pointing. And so you send coordinates up there, and you pick out your object of interest and gather data. So there are some. I think I understand the point of that question. There are some telescopes that only observe one patch of sky,
Right, exactly.
Sure.
and they
Yes.
hammer that for.
Yeah.
They get
That's it.
better, deeper data. Kepler did that.
Right.
Right.
Kepler was one patch of sky looking. There was a lot of stars, but it was still one patch looking for exoplanets, and because it had to go back looking for variations
Right.
in the host star.
Right.
So one set of data is not good enough. You got to go back and back and back, and then
compare all the different
compare all the
images so
data.
that you can- right.
So, and let me take this moment. Let's go over just who these people are. Okay. So James Webb was he was head of NASA during the 1960s.
Cool.
Yeah, but he was. I think he was the first person who we named a telescope after that was not a scientist. So I think there might have been
What?
some political stuff going on in the
Yeah.
back room.
That's kind of cool, though.
And
I
I think
kind
it
of
was
like
the first
James
naming
Webb.
before launch too, right?
Oh
Isn't that
yeah.
the first
Normally
time they've done
you
that?
name it after a person after launch.
Yeah.
Okay.
Just in case it
Right,
blows
'cause
up or something.
Yeah, that's
Right.
a bad luck.
Then
Like-
you blow your name blows up with
Right,
the
exactly.
thing.
Yeah.
Chandra was AXAF for a long time, and
I
AXAF
forgot all about that.
doesn't quite roll off the tongue.
AXAF.
But then it was
X-ray
renamed
astrophysics facility
Advanced
or something.
X-ray astrophysics
yeah,
facility.
yeah.
But then it was renamed Chandra after Subramanian Chandrasekhar, who is a very famous Indian American Nobel laureate who studied things like white dwarfs and stuff like that. So,
Very nice.
And he also did. I probably have a book
Oh,
by
yeah.
Chandra.
Yeah.
Let me see here. Hold on.
oh, look at
how
that.
funny.
There it is.
Yep.
Subramanian Chandrasekhar.
Yep.
Radiative transfer. So one of the more brilliant among us who.
Okay. I'm through. I can't even with you.
What?
I'm just
What?
done with you.
What?
Like, seriously.
What? You got issues?
Yeah, I got issues. Because I'm not an astro. This is the crap. No, crap,
This-
not crap.
it
But
is.
this is what you're reading?
Yes.
You're sitting around reading this?
Yeah.
Give me this for a
Yeah.
second.
No.
Here. Give me that for
No.
a second. What? I can't believe that. Okay, people at home,
Open any
I'm
page.
I'm just going to wait. Let me just open up. Okay, here's the page.
Oh, you're gonna read us to bed.
I'm going to read.
It's not
I'm gonna
light
read to
reading.
you. I'm going to
Chuck,
read to you.
bedtime stories
Listen,
from
here it is.
Radiative transfer.
Exactly. Principles of invariance. What is that? What is that?
Squiggly line.
What is that? Squiggly line. Squiggly line doodle thing. And by the way,
Okay, so
this just goes on for page after page
so
after
Chuck-
page of this. Some of the pages are just nothing but actual equations, just after equation after equation. I have seen Chinese
feel your anxiety.
newspapers that are easier to understand than this.
All right, so Chuck, if you write a book like this, you get a telescope named after you.
That is true.
So
Unbelievable.
he's wrote several books that really were the definitive word
Okay.
on those subjects, and they're still used in graduate school.
Yeah, and it was
That's
a
pretty
naming
wild.
contest. We actually had a contest for the naming, and it was a teacher and a high school student that picked the name Chandra as the winning entry.
Oh, very cool.
See, they knew.
So yeah,
Right.
they
Yeah,
knew.
clearly
They
you
did
didn't.
some excellent research and did not
course I
mind the
didn't know.
equations.
So we got to take a break.
Okay.
We have more questions coming up on the
Absolutely.
X-ray universe with Kim Arcand. I say it right. It's
You
French,
did.
but I'm
Yes,
Americanizing
you
it.
tried to French it was good.
I tried to French Arcand.
Yes.
Kimberly Arcand, Chuck Nice. We'll be back in a few moments. We're back. StarTalk Cosmic Queries, the X-ray edition. And I've got the leading visualization person for the Chandra X-ray Telescope, Kim Arcand. Kim, welcome to StarTalk. You're a first-timer.
Thanks,
I hope we
yeah.
get you back.
Yeah.
And Chuck,
Hey.
always there.
Yep.
You're there for me.
I am
love you,
always
Chuck.
here for you, my
love
friend.
You, man.
I love you too.
Okay.
Got it.
So what do you have?
Let's go to these people.
Chuck.
You just made this name up.
What? All right, go.
Adameroidia. I'm going to go with that. On Instagram, wants to know how many more stars can we detect with a Chandra X-ray Observatory than we can see with our naked eye? And can we detect exoplanet transits?
Oh, good. Well, we talked about exoplanets a little bit.
So can I reshape that question?
Yeah.
I look up at the night sky. The human eye can see about, in the total sky that is below and above you, about 6,000 stars, a few nebulae, with the naked eye. So how boldly different, if you could just turn on X-ray vision in a Chandra sense, what do you begin to then notice? What begins to pop?
I think it's more than just the stars. So I guess it's quality over quantity, right? It's not just the numerical number that we're going to be looking at, but more of like telling about what they are. So, for example, if you looked at a patch of the sky of Orion Nebula, for example, and you looked at that in
Which is the
optical
closest
light,
stellar nursery to the sun.
All right.
In the
maybe
constellation, among the
700
stars in
light
the
years away.
constellation of Orion.
Cool.
Yeah.
you can look at that in optical light, and you'll definitely see a lot of stars. But as soon as you look at an X-ray light, you're going to see the same tiny small patch. You might see 1,700 X-ray sources. But those aren't going to just be plain old stars. I mean, not that stars are just plain and old, but you know what I mean. You might see binaries, you might see black holes, you might see other types of these celestial objects. So I guess for me, it's just, it's not the quantity so much as the quality of what you're studying. And then you're also going to see diffuse emission, kind of like some of that hot bath that those stars might be sitting in.
So hot gases will radiate X-rays, and you're not going to see that with your naked eye, and you're not going to see it with your regular telescope either.
Right.
So the whole new world opens up.
Right. Another example would be something like Cassiopeia A, the supernova remnant, right? So you can look at that in optical light, and
Chuck, you're
you'll
nodding
see
like you knew all about Cassio.
But listen,
it's a good one.
what can I
It's a
say?
famous one.
What can I say? Even though it's not like it was it's not like it's something that is very esoteric. You know what I mean? To be honest.
A supernova exploded.
Right.
I forgot the year that happened, but there's a remnant of this exploded star. And we kind of knew it was there, but now Chandra gives us a whole other view of it.
A whole other world. It's really amazing to look at. I mean, you can look at it with optical light from the Hubble Space Telescope, and you'll see this beautiful filamentary structure. I'm a very visual person, obviously, so I'm lacking my images, but you'd see this nice, delicate filamentary material around the 10,000 degree mark, right? Kind of looks like a hollow shell. And so you can look at Cassiopeia with the Chandra X-ray Observatory, and it looks completely different. It's literally death come alive. It's this solid looking sort of
Death come
thing.
alive.
Yeah, it's death, but it's it does lead to future generations of
It's
stuff.
animated death.
Yeah, it is kind of way. It is moving. It's evolving.
Just go on.
Feeling poetic. Feeling very poetic.
Man, I can't. I got nothing.
But it's amazing because you can trace where the iron is dispersed and where the argon and the silicon is, and it just makes this incredibly gorgeous nebula to look at.
New stars
just
arrive
different.
from the ashes of that which has burned.
Exactly it.
Now, can I hang with y'all?
I like
Yeah,
that.
that's very nice. That's poetic.
Oh, that was very cool.
Yeah.
So is Cassiopeia, I always forget, is that the brightest source of X-rays in the sky, or is there another?
No,
maybe this
SCO X1 is.
Scorpios.
Yeah,
Scorpius
exactly.
X1.
Yeah.
Okay.
Yeah, but Cassiopeia is really bright, and it's great for
now,
Chandra.
Now you had to do it, didn't you?
What?
You had to go. I was cool with Cassie, okay, and then you had to go to SCO.
SCO.
And what is Scorpio? And what is
Scorpius, the constellation.
Constellation.
Okay.
Yes.
Now, I'm old enough. Okay. I'm older than all y'all. Okay. I worked at the Center for Astrophysics, which is a big X-ray place up in Cambridge, Massachusetts, as an undergraduate.
Nice.
Oh.
And
I didn't know
for
that.
my summer project, I worked on one of the earliest X-ray telescopes that were launched. So there was Uhuru, which was an X-ray telescope.
Right.
And
the receptionist on Star Trek.
Uhura. Yes.
Uhura,
That's your brother. Uhuru. But she was not the receptionist, dude. She was a lieutenant, first of
Right.
all.
Yeah.
This is true.
And a communications officer. So the first telescopes to go up, they just kind of looked for anything that gave up X-rays.
Right.
And then they created a catalog.
Sweet.
And they numbered the X-ray sources within each constellation.
Gotcha.
So by order of brightness. And so in Scorpius,
So-
the brightest one was X1.
So SCO X1 is, but is
And there's also a Cygnus X1 that's a good black hole candidate.
Yep.
Right.
And so when you see the X in the one, we got our first X-ray telescope.
Right.
And we got Cassiopeia was named before we had X-rays.
right.
So
And so now the detection of those. So
oh, by the way, those early telescopes, it was just to know that they're even there at all.
that's what I was going to say.
yeah.
Right.
So now you got Chandra.
Exactly. And that's what I
is-
love about X-ray astronomy is there are a lot of people on this planet whose whole lives have been the length of X-ray astronomy. The field is so young.
Yeah.
It really got going late 40s, early 50s. And then by the time
Well, from
I
when they had
was-
detectors, yeah.
Exactly. And by the time I was born, there was a good one detector on Skylab. By the time my kids were born, Chandra had launched and XMM Newton was launched. And now they're working on new generations of X-ray
So
telescopes.
Chandra
and
was
detectors,
92
so.
or 99?
99.
99.
So
2019 is the 20th anniversary.
That's 20. Okay.
Yeah,
Yeah.
this summer.
Now before that, you're looking at images like 100 times kind of dimmer or fainter,
much
right?
fainter. And I mean, it started out like looking at the sun to just get X-rays from the sun first because it's a nice nearby target.
The sun
and
bright
then-
enough, you think?
Exactly. Chandra can't look at the sun because it's so bright.
Because it's too
So
bright. Okay, yeah.
It would
See?
like fry Chandra off. But
I can look at
Yeah.
the sun. Never mind.
oh right, no one should be looking at the sun. How's that? Especially not Chandra. But yes, and then with like Uhuru and Einstein, like all these other missions, it's just been an amazing, like compact amount of X-ray astronomy that's happened in just a handful of decades.
But it took a normal course of evolution. So
It did.
You first got to know, you want to learn that there's any kind of source of X-rays
something
at
to
all.
detect. Exactly.
Here, there.
Right.
That they're blunt instruments, right? Then you kind of wonder what it is. You might do some calculations, but still you don't know. And the later generations, you say, now that I know they're there and I know what kind of signal it's giving me, let me devise a detector that can more precisely measure that,
Right.
Or measure something dimmer. And so, like you were saying, you see the dimmer ones, you get more precision in your image.
Right.
You start making X-ray images.
Right. And now Chandra's images are so sharp and beautiful. I mean, when you're looking at things like supernova remnants and it's just so much detail that you're seeing, never mind what the next generation of X-ray telescopes will be able to do, like
Wait,
100 times more sensitive.
Will the next generation say, back in 2019, Kim thought she had high resolution images.
I'm sure. I hope they do.
But she had nothing.
We had nothing. Yes, that would be perfect.
That would be
would
great.
be the best thing.
The best thing if you were obsoletifified.
Yes.
By
Absolutely. Does
better
everybody want
telescope.
that?
Yeah.
Yeah.
All right, should we go another question? Let's
do it.
Let's do this. This is Chris Cherry from Instagram says, "What is the next light spectrum we'll be observing in the universe, or observing the universe in?"
All of them, all the above. I mean, I guess it depends on what they mean by their question. If they mean what's next to be launched, I mean, hopefully the James Webb will be the next to be launched, and that'll be infrared.
Right.
And then beyond that, it's whatever's in the budget and what other agencies are able
Great
to
answer.
do.
Whatever's in the budget.
Right?
That's funny.
I mean,
I love
it's,
that answer.
That's
Great
funny.
answer.
it's true.
Yeah. What's the next spectrum? Whatever's in the budget.
Yeah.
That's the next.
But ideally, all the light. We want all the light.
Right. Very cool.
But here's an interesting challenge. Okay, so let's. So radio waves have very long wavelengths,
Right.
And one bit of evidence of that is those who remember televisions that had rabbit ears. They are detecting radio waves as television signals, and the length of the rabbit ear is commensurate with the length of the radio wave that it's trying to capture. So that's okay. So suppose you want to detect a radio wave that's a meter long or 10 meters long or a kilometer long. How are you going to detect that? You need a detector that is at least that size.
Right.
So you can get a whole wavelength in there, or at least half a wavelength. You need some fraction of that wavelength hitting and being able to focus it. Suppose there's something out there that makes a radio wave that is the diameter of Earth's orbit around the sun. Who's detecting that? So there could be phenomena in the universe that is washing across the entire solar system, and we don't have detectors that can pick it up.
Wow.
I do like radio waves. If I had to pick a second favorite besides X-rays, I think it would be radio waves.
That's a nice pair of waves right there.
Yeah, they really
Yeah.
are. They're very complementary.
Yeah.
It's true, even though
Yeah.
they're on opposite parts.
They're opposite parts, but they're good.
Opposites attract. I mean, it really does.
Plus, they're highly used in our culture. Radio
this is
waves
true.
That's
for
true.
communication and X-rays,
X-rays
for
for help.
medicine. Health,
Yeah.
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 Very, very cool.
All right.
Could there be Julie H, who comes to us at Time Traveling on Twitter. And I like that. She says, could there be technology like Street View on Google Maps that visits various points, just points in the universe?
Oh, that's
Interesting
a great
question, right?
Yeah. So we have Google Mars, I think it's called. You can look that up, googlemars.com, or maybe it's mars.google.com, whatever. That it's almost like Street View of some of the data on Mars, and that's really amazing. Getting more three-dimensional, which I think is the point she's kind of getting at there, data of our universe is really hard. Once you're going beyond nearby objects in the solar system and you're going farther out past the stars, it's really hard to get some sort of usable dimensional data on that to then turn into like a 3D model that you can tour in like a street view type of map.
So you think you don't do 3D modeling for Chandra?
We do.
You do?
It's just hard.
Oh, okay. Okay.
But we do, yeah. Actually, I do
We
have
do things
a 3D
not
model here.
because they're easy,
But because
they're hard. So you brought to show and tell.
I did bring something for
Okay.
show and tell
So
because,
this is-
again, I'm a very
this is an
visual
audio
person,
show.
which does not help the audio folks.
Right.
I know.
But
we can describe it.
Yeah, so it is a kind of globular-looking structure, and it has many different nodes that are jutting out from it. And
It looks
then
like a tumor removed from somebody's
it
body.
really
Yeah,
does.
but there's a reason for that.
If you've ever,
You know, it looks like fossilized, not calcified coral. That's what that looks
very
like.
Yes,
good.
yes, it does.
that good?
Yes.
Wow,
so
Neil,
why it
that
looks
was excellent.
biological,
So
though,
it's-
it's because we
Why
actually
it's what you
used
say?
why it looks biological. It's because we actually used brain imaging software adapted from some local area brain scientists in the Boston area to make it. That we use their software, so that's why it looks
Interesting.
more brainy-ish or biological-ish than you would probably expect.
That's funny
otherwise.
because before we sat down, I picked this up and I said, "Is this like a firing neuron?"
Right,
And
right,
so weird
right,
that you
right.
said that it
So
comes
there's a
from brain
lot.
imaging.
Yes, yes. Well, I mean, if you look at visuals from the micro versus the macro, now you're speaking my language because of my biology background, but you can see so many similarities in the way that you process those data, right? But what you're holding is a 3D model of Cassiopeia A, our good friend that we were talking about earlier, the supernova remnant.
That's so cool.
Yeah, 10, 11,000 light years away, and you're able to hold a version in your hand, essentially because of the Doppler effect. Right?
So did you 3D print that?
Yeah, this is 3D printed.
Okay.
Yep. So we worked
So the
with,
Doppler effect gives you depth information.
Right, exactly.
Okay.
So Tracy Delaney, she was the scientist who first worked on this. She was at MIT at the time, and she was essentially figuring out what information was moving away and what was moving towards.
Was she with their imaging lab? MIT has a big, famous
No,
imaging
she wasn't
lab.
actually. This is separate, but we hooked her up with the folks who were working on the medical imaging software translation, which was called astronomical medicine. And
That's cool. I
This
like that.
was the result.
I like that,
Yeah.
that hybridization.
Yeah.
This
So
is
it's
fascinating.
cool.
I
Yeah.
love it.
So scale is an issue, though. Obviously, when you're holding something that's small, this is like 4 inches across for those listening, maybe.
Okay. Well, we can do, maybe we'll photograph it and
Yeah, I
we'll
was
post it.
gonna
say,
We'll
we'll
post
post
it
it.
next to the
But
the audio.
in real life, it's like the surface area is maybe 40 million billion times the surface area of our sun and planets. And you can toss in Pluto if you like. It doesn't matter.
yeah,
That scale.
Pluto. Yeah, or toss it out. It doesn't matter.
But yeah.
All right.
I
So
buried my
3D's
hatchet
hard.
with Pluto.
Oh,
Me and
good,
Pluto
good,
were
good.
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 All right, Chuck.
Only you have to bury the hatchet with a
Pluto.
with a dwarf planet. I was about to say planet.
With a hound dog.
With
Yeah.
yes, exactly.
Bloodhound, I think.
But yeah. All right. Do we have time for
But
one
let me
more?
hear the question.
All right, I'm going to give you the question. This is Tom Ricks from Facebook. He says, "Do you think virtual reality will ever allow the human brain to completely comprehend the immense distances between planets, stars, and galaxies, or is this something that we'll never fully grasp?"
We will answer that after this break.
Nice.
See what I did there?
There you
That
go.
was nice.
It's called a
That's
tease.
nice.
It's called a tease.
Ooh.
And this is
That's good. That's a fun
StarTalk,
question.
Cosmic Queries, X-ray Astrophysics Edition. We'll see in a moment. StarTalk, Cosmic Queries, X-ray Astrophysics Edition. We're celebrating the 20th anniversary of the launch of the Chandra X-ray Telescope, one of the great observatories up there with Hubble and James Webb and the rest of them, each of them targeting their window to the universe.
Nice.
I got Kim Arcand.
Hello.
Yes. And Chuck.
Yes.
So we left off.
Right.
We left people dangling.
Yes.
Where can virtual reality help us comprehend the scale of sizes and distances and things? Let's make this a more broad visualization question.
All right.
Part of your job, Kim, is to get people to see things we don't otherwise see.
Right.
Or to grasp scale and texture and phenomenon that is not otherwise accessible to us looking on our Instagram account.
Right.
So what role do you see that you play in getting us closer to the universe?
Oh, that's a great question. I think mostly my job is to just sort of oversee all the various visual platforms that we can take Chandra data to. I mean,
Oh, it's not just photographs.
not just images. Yeah. I mean, Chandra, one of the great things when you have a telescope that's been up there for so long is you just have a fantastic archive of data to work with. And as technology has developed in other sectors, you have all of these new platforms to try it out with. So we were talking about 3D printing earlier and the idea of what you do with 3D models.
So you got to stay current with all that.
You do.
And exploit it in your
Yes.
service.
When I started working for Chandra, Cassiopeia A was one of the first objects we ever looked at, right? And it was beautiful in a flat 2-dimensional image, and I was amazed. Never would I have imagined, fast forward 20 years, and I'm holding a version of it in my hand or walking inside it in virtual reality. Like those technologies were not a reality at the time. So with things like virtual reality or augmented reality, mixed reality, data sonification using sound, there are all of these ways to
Data
take
sonification.
that. Yes.
So add another sense
Yes.
to the interpretation
So,
of the data.
for
Is this also
example-
good for blind people?
Exactly. Dr. Wanda Diaz actually has done a lot of work around that. My kind of perfect world would be a virtual reality application where you have the visual, of course, but then you have the layer of sound that's also spatially attached. So you know where things are. And then also like a haptic layer. So you can
I don't
actually
know what that
feel
means.
vibrations.
Haptic.
So like, when your phone
Why don't you just say
vibrates.
touch?
Because haptic is a much
Touch
cooler
layer.
word.
I know. It's called haptic technology.
Okay,
That's
okay.
what we use. I don't
Okay.
know. But yeah, it's essentially by being able to feel those vibrations as you're moving through the remnant, right? So there are all these applications, none of which were around.
So moving through the
1999.
remnant. So we have the 3D model, and you become a journey. You journey through the
it.
model.
Exactly. Exploring it. Now, the scale is
Oh
still
my God,
hard,
they used to have that
right?
at the Franklin Institute. It was a heart.
Yeah.
Oh, yeah.
right, yeah.
Yeah,
Yes,
and
yeah.
I remember
The
being-
living heart.
The living heart.
Yeah.
You would walk through the heart.
Right. So think of that except virtual, right? But then having cues of sound and touch. And it's a wholly different understanding and experience of that information. Now, going back to the question of scale, I mean, as soon as you get out of Earth-size scale and even smaller than that, it's really hard for human understanding and relations of what we know. So whether that will actually help people understand and comprehend some of these vast scales, I don't know. But
And it doesn't.
helps, I think.
It might help, but here's the thing: it's just not. Everything that we see, we imagine on the scale that we see it.
Yeah.
Right,
Because that's the
exactly.
scale
That's
in
us.
which we
That's
live.
us.
Exactly.
And so
The scale in which our senses were forged.
Right.
Correct.
exactly.
Yes. So the problem is that even if you were able to demonstrate it, your brain would be resistant to actually then revisualizing it that way because you're so used to looking at, the world through the eyes that you have,
Exactly.
which is like Neil does this thing where he shows, which the first time I saw it, because he did it for me, I was like, get out of here. And he showed me just where the moon and the sun and the earth are.
Right.
And it was like
Relative to each other.
Relative
Yes,
to each
yes.
other. And we just did it with like a basketball and something else. And we did it in a regular room. And I'm like, you got to be kidding me.
Right.
Yep.
Like, you know what I mean? So even being able to see it in that.
And those are just planets.
And those are right.
Yeah,
These things are so
that's a
much
backyard,
bigger.
dude.
Exactly.
We're not
It's
talking
just
about
a speck.
galaxies.
Right.
Exactly.
Yeah, that's crazy.
So I don't think the human brain could ever comprehend those vast scales.
Yeah.
It's just too much.
Cool.
Yeah.
Oh, man. This is good stuff. All right.
I got another quick one just while we're there.
Yeah.
You might ask, you see all these stars in these photos, and you say, will stars ever collide? Well, they do rarely, but they do and they can. And it's interesting when that happens. But to appreciate how rare that is, if there were 4 bumblebees in the United States flying randomly, there's a higher chance that 2 of them will accidentally bump into one another than for 2 stars to collide in a galaxy.
Oh, that's a good
That's a
analogy.
great
Yeah,
analogy.
That's a good one.
That's
4 bumblebees.
Just 4 bumblebees.
Bumblebees.
Yeah.
So you look at their size and the
Right.
distance between them. That's kind of what you're getting. The size of a star relative to the distances
Distance
between
Right,
stars.
right. That's a good one.
And by the way, if there's only 4 bumblebees, we're all dead because
Yes.
there's no food.
There's nothing gets pollinated.
Nothing.
All right. I hadn't thought about that.
Right.
Not feel guilty, dude. All right, next question.
All right, this is
before we go to lightning round.
Here we go. Jonathan Gallant wants to know this. Hey, it's Jonathan from Edmonton. How far away from? You know what? We did this already, but I'm gonna give it to you anyway. He's taking it one step further than the last question as a follow up. We'll call it. How far away are we from a Star Trek like stellar cartography room like they have on the holodeck
in the next
So I like
generation.
this
in the next generation?
Yeah.
Next generation, the holodeck. Yeah,
I really like that question.
it's a great question.
We are actually just starting to experiment with holograms.
Oh.
But screen-based holograms, so not just sort of appearing in the
Not
room.
help me,
Not quite
Obi-Wan
yet.
Kenobi, you're my
Not
only
yet.
hope.
But even screen-based holograms.
That was really geeky.
I mean,
oh my gosh.
but that was good. It was
Oh my
perfect.
gosh. Oh my gosh. I didn't know you had it in you. Good.
It's there. I mean, and I think with like missions like Gaia and others, building this sort of nice 3D map. I mean, the universe is 3 dimensions.
So the Gaia mission
right?
got 3D data on millions of stars.
Right.
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 In our galaxy.
Right. Our world is 3D. So being able to bring some of that 3D nature into a way that we can visualize, understand it, and then explore it. I think it's really important. I really do. And it's awfully fun.
Very cool.
Yeah.
Excellent. Excellent. I don't even know if we have enough questions left
for a lightning round. Well, then we can just chill with them.
All right, let's chill with it. This is
Well, let me slip in a question here.
Go ahead.
So, can we just go back to basics?
Yeah.
When you're going to make a simple color image of something that has no color,
Right. Yep.
and you're using your X-rays to do so, what are your steps?
Well, so first we get the data from whatever object it is. If we want to use Casset as our example,
That's the favorite object of the day.
It's just the favorite object. It's actually one of my favorites, if I want to admit it. But we first get the data in. It's when it first comes down, it's actually transmitted and coded in the form of ones and zeros. Then it goes through some software, and then it's translated into a table that shows the X and Y position of the observation, the time and the energy of each of those packets of light that struck the detector during the observation. Then it's like yet more software.
Oh, by the way, we could measure visible light in the form of energy. We just don't. The way we do it is we measure it by color.
right.
So, this is a blue photon and this is a red photon, and we just say it's blue and a red. But if we did a Chandra thing on this, we'd say this is the higher energy photon, this is a lower energy photon, and the blue would have higher energy than the red.
Right.
So it's really the same thing, but they have a whole other. The detectors measure this in energy, so the vocabulary and the steps are shaped for that.
Right,
Okay.
exactly.
So sorry to interrupt. I
Yeah,
just wanna
no.
slap that in there. Okay,
So,
go.
More software, and we finally get the visual representation of the object. And I like to use that term for a reason, because I think there is this idea that these images of the universe are giant cosmic selfies, you know what I mean? Snap done, and they're not. They really do take people like me or like whoever to do the creation step, because it is light that you can't see. So then you create the visual representation of the object, and then you refine it. You have to get rid of artifacts or bad bits of data. You have to smooth it. You might have to crop in the field of view that you need, and then usually the last step is color. And I like to slice and dice an image by energy level, essentially. So the lowest energy X-rays will be assigned red, the medium green, and the highest blue, unless we're adding it to optical image from Hubble or Spitzer infrared image.
Right, because
and
that means you
change
can't
it.
take their color.
Exactly.
Yeah.
You have to share.
You have to share the colors.
Sharing is very
We only have Roy G.
important.
Biv. You got to,
Sharing
spread
is
the
very
love.
important
Sharing
in
is
astronomy.
caring.
Exactly. Sharing is
Gotcha.
caring. And then you compile it together and you get your color image. All stuff you couldn't see. Even if
Right.
it's the optical range, most of this stuff is you can't see because human eyes are so puny.
Feeble. Yeah.
Wow.
Yeah.
That is incredible.
Yeah.
That's incredible. So you're actually layering this stuff one on top of another to form the image itself.
Right.
That's pretty
And by
cool,
the way,
man.
your retina is doing that. So the cones
Right.
of your retina,
Right, yeah.
they're red sensitive cells, they're green sensitive cells, and they're blue RGB.
Right.
And light comes in, it triggers one cell or another, depending on how much energy it has. But we say it's depending on what color it is, right? I mean, it's an energy thing. It's all about energy.
Right.
And so you trigger a certain amount of the red, green, and blue. And if it's more red than blue or more blue than red, it shapes what color it turns out to be that your brain interprets. So it's the same thing as your eyes.
Wow.
Yeah.
Or your computer screen or
Right.
whatever.
Yeah. That's wow.
Yeah.
Have you ever looked at RGB instructions in the computer code? It's just a level of
haven't.
how much of one
I'm going to be honest. I have not. You know what I go with? Default.
Safe place.
You don't go in and program it.
I know.
Okay, so the point is, if the colors are, you can make arbitrarily any color once you have the RGB.
Right.
It's just a mixture of those three, and that's why. And it only works that way with light. Don't try that at home with paint.
Right.
You mix RGB paint,
Yeah.
you get mud.
You get mud.
Right.
Right. Yeah,
Okay.
exactly. Yeah. Now, I did know that. I just.
And my boy figured that out.
Who?
Isaac Newton.
Oh.
Isaac
really?
Newton. Yeah, he knew that people kind of maybe figured that white light can make a spectrum.
Right.
But he took the spectrum, put it back through a prism, and it made white light.
Right.
And that freaked people out.
Yeah.
How do you get red, orange, yellow, green, blue, violet, and get white?
Right. Right.
Yeah, yeah.
Yeah. Well, thank you, Isaac Newton. If it weren't for him, I
My boy
would
Ike.
not have had a livelihood. Not a livelihood, but I wouldn't have been sustained growing up because my father was a printer, and
Oh, I didn't
that's
know
what
that.
printers
right,
do.
right, yeah.
Yes.
They actually take light and they mix it to create color.
CMYK.
That's exactly
Instead of
right.
RGB.
That's exactly right. And that's from that exact same principle that you just said.
There you go.
Which is that's excellent, man. Very cool. Look at that. See how science is a part of your life and you don't even know it? Here I am eating because of Isaac Newton.
It's a stretch, but it's okay.
But that is kind of the whole point of the show, Chuck. Okay? You're acting like that's some new revelation about what we're doing here.
Okay.
Chuck, we got 2 minutes. Let's see what we have.
All right, here. Skynet is Aware from Instagram says this. So Chandra was originally launched in 1999. How has the technology advanced since it was launched? Do we have better technology 20 years later that is more sensitive? So...
okay. Can I ask that differently?
Okay.
Sure.
Okay, you ready?
Yeah.
Okay. At what point do you say, we've got such better technology, let's drop Chandra in the Pacific Ocean and put up the better technology because you're spending money on something that was conceived and designed not 20 years ago, but 25 years ago when it was still on the drawing board.
I mean, if you have an embarrassment of riches in that situation, fantastic. But that's not the reality. So we don't.
You don't have a way better X-ray telescope
ready
sitting
to go
in the wings?
Right there. No,
Come on, 20 years ago?
Well, that's expensive.
1989?
It's expensive.
The Macintosh was 5 years old.
You have to take turns.
There was no smartphones.
Yes.
Wow.
But Chandra is still cutting edge. It's still it's just an incredible piece of equipment still. I mean, they had to smooth Chandra's mirrors so much. Like all the technology that was necessary to create that has then actually led to all of these fantastic spin-off technologies that we get to benefit from every day in medicine, in imaging, in
focusing X-rays is a big thing.
I mean, it's huge. Like there was so much work that had to go into figuring that out. So I feel like we can write off that for a while. I'm just saying, don't put Chandra in an early grave. It's doing beautifully.
Okay. All right. That's very cool. Very cool. All right. Do we have time for another one?
Can I end with a story?
Let's
story,
do it.
story time.
Story time. Okay.
Story time.
Yeah, good. Let me get rid of these stupid questions. No, I'm joking.
Okay. So there's a guy. His name is Riccardo Giacconi, generally considered among us to be the father of X-ray astronomy.
Yep.
Okay.
And he knew that if you want to see X-rays, you have to do it from above the atmosphere because X-rays don't make it through the ozone and other particles in our atmosphere. So you need something above the atmosphere if you're going to see the universe in X-rays. Well, if you're going to launch something, it can't be too heavy because it's expensive to launch heavy things. It's got to be light. It's got to be portable. So he was one of the founders of American Science and Engineering, a company based in Cambridge, Massachusetts, that pioneered small portable X-ray detectors. When was this? In the 1960s? What was going on in the 1960s? Oh, they were hijacking planes to Cuba. People were taking guns on planes. Congress said, we need a way to stop guns getting on planes. We need X-rays at airports. Bam! We have American Science and Engineering providing the first X-ray detectors at airports, enabled as these portable devices because they're trying to put them on a satellite into orbit.
Wow.
And he would ultimately get the Nobel Prize, as you, Kim had introduced him earlier in the show. And I was on the committee, the presidential committee that awarded him the Presidential Medal of Science. And when you get the Presidential Medal of Science, everyone goes to the White House. So I get invited to the White House. And here comes Riccardo Giacconi to the White House to get the Presidential Medal of Science. And you go through the security house before you get into the White House itself. And what does he walk through? An American Science and Engineering metal detector.
Wow.
And it was like,
and does he have a metal hip or a plate in his head? That would be awesome.
And then they tackled him to the ground. I just thought that was so.
Yeah.
It brought closure
Yeah.
to the fact that the president is being protected by technology that he helped pioneer, and he's getting the Presidential Medal of Science for having pioneered just that.
X-ray astronomy is a gift that keeps on giving.
Well, there you go.
And I tell that story in Accessory to War with my co-author, Avis Lang.
Nice.
And just it's astronomy technology affecting security.
It's one more way where our penchant for trying to destroy one another has led to a modern day marvel.
Happy note.
We got to end it there, Chuck.
Yeah.
So Kim Arcand, thank you for coming on
Thanks,
StarTalk. Your
yeah.
first time. I hope we can get you
It's
again.
fun.
You're not that far away. You're
No, not at all.
You're in Providence.
Yep.
Providence, Rhode Island.
Indeed.
Yes. And
Yep.
so it's great to have you on the list.
Thanks.
Chuck, always good to have you.
My pleasure, Neil.
You've been listening to, possibly even watching StarTalk, Cosmic Query's X-ray Astrophysics edition. I'm your host, Neil deGrasse Tyson, and as always, I bid you to keep looking up.